Welcome to the Develop Yourself podcast, where we teach you everything you need to land your first job as a software developer by learning to develop yourself, your skills, your network, and more. I'm Brian, your host. There's one thing that bootcamp grads and self-taught developers generally lack that computer science grads have. It is a knowledge of data structures and algorithms. And I'm not talking about some insane amount of knowledge here. I'm talking about basic knowledge. I fell into this camp. For the first 3-4 more years of my career, I didn't know what the hell DSA was. I didn't know data structures. I didn't know algorithms. And I thought, why would anybody need to know this stuff? Just for interviews? And partially, yeah. If you want to interview with the biggest tech companies out there, you better know data structures and algorithms. And then I hear this online way too often. People say, you don't need to know this in real life. It'll never come up. All you need to know is just how to code, and that's it. And that is completely wrong. So if you have a basic understanding of data structures and algorithms, not only are you going to pass interviews and be way more confident, you're going to understand how most solutions have been crafted. Because most of what we do as developers is taking an algorithm or a data structure that's already been invented and just leveraging it to make sense for us, for the thing we're trying to do. The biggest problem I see when I've worked on a team of junior developers, or me as a junior developer, was basically reinventing the wheel all the time and come up with these wacky solutions to problems. And it's just because I didn't have an understanding of like really basic stuff. I'd also make really inefficient solutions because I just didn't understand, oh, that's not just free, right? Like you can't make something work and not think, what if I have 1 million users come to the website? I'm going to do an episode on that later, but all the biggest mistakes I've made as a developer, and some of them are pretty funny in retrospect. Some of them not so funny. Some of them really showed a lot of my ignorance. Anyway, what we're going to do is break down very basics of what is an algorithm, what is a data structure, and then I'm going to go over a little bit of math for developers. Don't get scared. It's like shorthand, easy math. And then go over a very common searching algorithm called binary search. And by the way, go to those show notes, get the DSA study guide for those of you that want to crack those massive tech company interviews, or you just really want to get good at data structures and algorithms on your own. Maybe you're doing a course like CS50 or something like that. And that's a really long, intense course, and it's a little too conceptual for my liking. I think it's great overall, especially now that I know a lot about code. But if you're just starting off, maybe don't do that. Colt Steele has an excellent program on Udemy. I've taken it, really helped me out. And I spent $10,000 a few years ago studying data structures and algorithms. And you might be thinking, whoa, what the hell did you do that for? Weren't you like working as a developer back then? And yeah, I was. But I knew I was limiting myself. I knew that I was severely limiting myself by not knowing this stuff, not only in interviews, but because my work. I was working with people that understood things like, oh, there's a solution to find the shortest path between two distances in a graph. Oh, there's a solution for how to make that if-else statement a little more concise. Oh, there's a solution to all these things that I had just been thinking, well, they just must know more than I do. And they did. They knew that there were already solutions to these things. So without further ado, what the hell is an algorithm? It's a recipe. Hope that wasn't too lackluster, but yeah, just a recipe to do something, a repeatable way to do something. So you want to cook cookies, right? You want to bake some cookies. And what would you do? Would you just wing it? Would you just throw some potatoes and some flour in a bowl and be like, hey, I got these cookies? People would be like, that sucks, dude. You made potato cookies. What the hell is wrong with you? That's what happens when you're always reinventing the wheel. You're starting from scratch, doing your best, adding potatoes in your cookies, and being a fool. Don't do that. No algorithms. Algorithms are a repeatable way to do something, a recipe. When we talk about algorithms, they're like a step-by-step procedure for solving problems. And if you think about something like the YouTube algorithm or the Spotify algorithm or whatever, some social media site you use, what we're really talking about is how do they determine what data to feed you next? What video are they going to feed you next? What image are they going to feed you next? TikTok's algorithm is different than IG's algorithm. And what we really mean is the way that they've structured their systems to offer you the next thing they think you're going to like is based on an algorithm. They look at a bunch of data and they determine based on that data, a repeatable way to give you something you like. And they change these algorithms all the time. That way people are always trying to game the algorithm. They think it's some like mystical thing out there. And it's kind of mystical because it's hidden from us, But in general, it's just a computer program that looks at some data and some metrics and decides, oh, people watched a video for this long and people in this bracket that we've categorized them in like it. Well, let's feed it to more people. And then they change the algorithm when people start to game it. When people kind of figure out like, oh, I can add this word or do this in my video and I can kind of game the algorithm, then they change it up. That's it. Now, the algorithms that you are going to work on as a developer and that you're going to interact with, things like arrays, if you're a JavaScript developer, objects, something you might be familiar with if you're a JavaScript developer. There's sorting and searching algorithms. If you have a lot of data and you want to find the middle number or something, or the highest number or the lowest number in a large set of data, there are algorithms to do that. Think about when you get in your car and you go on Google Maps or Apple Maps or whatever, and you want to know the shortest path between your house and that cookie shop that doesn't sell cookies with potatoes in it, and you want to know how to get there. Well, it takes the shortest distance between the 2 points and uses an algorithm in the background to do it. Now, you might be thinking, are they all using the exact same algorithm? No, they can use and take advantage of one that's already there and then add more to it. They can put their own twist on it, just like a recipe. By the way, if you are writing code and you have a repeatable way to solve a problem, you, my friend, are the author of an algorithm. So it's not this mystical thing out there. It's something you just do as a developer. There are really common ones, and you can look up a couple. Dijkstra, very famous pathfinding algorithm. There's things like depth first search, breadth first search. These are ways that you can understand how to efficiently travel in a maze. There's all sorts of really cool ones that if you just understand what they are, you can say, oh, maybe I can use this for a problem I'm trying to solve, right? And data structures go hand in hand with algorithms. What a data structure is, think about like a toolbox, and you are a plumber and you have a toolbox. How would you organize your toolbox for work in the morning? Would the plumber organize it differently than the car mechanic? Probably. They both have a toolbox, but they've organized it so that they can easily access the tools they need really quickly. Same thing with a data structure. If you're a JavaScript developer, again, like you could use an array or you could use an object. They have similar properties. They can store data. Now, how they store it is very differently. They're still storing maybe numbers or strings or whatever, but the way they store them is differently. Same thing with any other data structure. Some of the most common ones you're going to come across: linked lists, binary trees, binary search trees, heaps, stacks, queues. Again, all in the show notes. Grab it, check it out, go from there. It is a comprehensive guide. But again, if you don't want to get into FANG, one of the big top tech companies, don't worry about that kind of stuff. And at Parsity, I'm introducing all this in the curriculum. I'm actually going to do that this month. It's going to be really fun. I can't wait to do it. Doing mock interviews and doing way more data structure and algorithm stuff. So that way people don't have to feel intimidated or like they need to avoid these kinds of interviews. So I want to make it so if you want to go to Google, hey, we got you, right? If you want to go to Google or if you want to go to Meta whenever they start hiring again, then you should be prepared to do that interview, right? So let's get into a little bit about how we determine the efficiency of an algorithm and a little bit of developer math. Developer math. Hope I didn't scare you there. So do you need to know math to be a developer? No, not really. I studied a little bit of math, like my third or fourth year into writing code, because I thought it was interesting. I wanted to learn a little bit about statistics and algebra. And I got to tell you, did it help? I don't know. I probably should have stuck with it longer. But if there's one form of math you need to understand, it is big O notation. This is a way to analyze the efficiency of an algorithm. So you have this recipe. You want to understand how efficient is this recipe I've created? How bad will it get if I have a lot of data, right? You might write a function that looks in an array and it looks at the middle, it gets the middle number in that array. And so what do? You look over every single item till you get to the middle. Works great. What if somebody passed in an array that had 1 billion characters in it? Would that be sufficient? Would that be a good idea to look at, half of 1 billion? A user's computer might slow down. It might crash. I kind of infamously at a job I was at didn't understand that, it's not just free to write a function, that they need to be efficient as well. They can't just work, and they can't just work for a small sample set of data. They should work for a large set of data. Think about this. You have a computer program. Does it work when you have one user? What about 100? What about 200? What about a million? What about a billion? Right? You're thinking very differently when you're thinking scale. And big O notation is a way to understand scale. So when you write big O notation, this is something like that you just would do in your head. You wouldn't have to like make it very formal or anything, by the way. You would just think, if this function or this data grew by X, how slow would the algorithm be? And you can express that in a couple ways. You can have O of n, so it's an order of n. N being the input is in an order of n squared. Input, times the input. So how slow will this thing run? So for example, if we go back to the idea of having like a dictionary, and you say, how long would it take you to search for the letter Z or the word zebra in the dictionary? Well, that would take order of n operations if you did it the really slow, dumb way, right? The really slow, dumb way might be to be looking at every single word in the dictionary, going page by page by page by page. And so that would take you order of n operations. So at worst case scenario, and by the way, big O always is worst case scenario, you'd be looking at every single page in the dictionary until you got to the very last thing, which is some word I don't know. Let's just call it zebra, right? Order of n operations. What if instead you were smart? Because the way that you look in a dictionary is not by doing that, right? You don't look in a dictionary by going page by page by page. We're smart. I hope you are. I think you must. You're probably good looking and smart if you're listening to this podcast. I'm just guessing. I have to assume, right? So if you are a smart, good looking person listening to this podcast, searching for the word zebra in the dictionary, you do what? You open up in half and then you say, I'm on the word, I don't know, cat with a K or crispy. I don't know, whatever. You're on some word with a K and you say, you know what? I know that Z is after K. So you split the dictionary in half again, maybe, and then you're some other word like R, like for rabbit or something like that. You say, oh, and then you keep splitting in half. How many operations have you done this time? Well, every single operation, you've cut out half of the choices, right? You've cut out half of the choices at each step in this operation you've done to find the word zebra or whatever. That will be described as order of log n. That's a way to describe when you basically cut down your set of possibilities by half each and every single time. So we have order of n, looking at every single one. Order of log n, basically cutting in half your choices at every single step. And then we have something like n squared. Now, this might be when you look at a word and then you look at every single other word, which might be part of that word. So if you look at like aardvark and you say, okay, I'm on the word aardvark. Now, let me look through the entire dictionary, every single word that might be included in the word aardvark. And so you'd look at, I don't know. I don't know what else would be included in aardvark. You go to bear and you'd look through the whole dictionary and say, oh, well, ear is included in bear. You say, cool. Well, now then imagine doing this. So for every single word, you'd be looking in the entire dictionary over again. Can you imagine how long that would take? You'd probably be doing that for the rest of your natural life. And when you think about a function or a program in coding that does that, you can begin to see, oh, wait a second. If this is order of n squared, meaning this will run, let's say my input is 100, this will have 100 times 100. So this will have 10,000 operations happening. Well, that might not be good. What if it's 1,000, 1,000,000 operations? And you start to see, well, maybe I need to rethink this. Maybe I need to rethink how this works. So I didn't know this kind of stuff when I first started writing code. I wrote something that was like O of n cubed, and it brought down the system to a halt when we had more than like 20 users. With one user, me, it worked great because it's like, oh, one to the power of 3 is 1, right? 2 to the power of 3 is 8. And you start doing something like 10 to the power of 3. It's, I forget, like, I don't know, 10,000 or something like that. Or 1,000. And so it just grows exponentially. And so knowing this, if I had known big O notation or just kind of how to determine the efficiency of this algorithm, I wouldn't have got in this really, really sad place and been embarrassed. In that way, in that day, my manager said, hey, do you know what big O notation is? And I said, no, what is that? He showed it to me. I'm like, oh, well, damn. Wish I'd known that. Now let's get into binary search. We kind of talked about this with the idea of the dictionary. So binary search is a famous algorithm for finding a value in a sorted array, or in some, if you have a sorted set of data, then you should be using binary search. Just like with the dictionary is a perfect example of something that's already sorted, and you can find something really efficiently using binary search. So binary search would be order of log n. That example we talked about when we say, you know what, we have something that's sorted, we know that we can generally be splitting up the data in half at every single step. So again, we're looking for the word parrot or something like that. We open up the dictionary to the middle and we're on the letter O. Like we're on, order, something like that. And we think, okay, well, is parrot before or after order? Oh, it's after order. We throw away the half of the dictionary. We're never going to look there again. We already know we're done with that part. So now, because it's ordered, we know that we can now, maybe you can go open it in half again, or you could just open it a little bit and say, hey, now I'm on the letter P. I'm on parrot, done. You've taken an operation that could have been, 10,000 operations long and got it down to like 2 or 3. That is the power of binary search. So these aren't just like these conceptual things that like, oh, who cares? When will I ever have to know that kind of stuff? This stuff can come up. If you're doing things like data retrieval, which guess what? That's kind of what we do as developers. We look at data, we retrieve it. We try to retrieve it in an efficient way because users expect speed, lightning speed on the net, right? When you go to Airbnb or Instagram or YouTube, you don't want any lag at all. So think about the people that had to construct that. And you may be thinking, oh, I'm a front-end developer. What do I care about that kind of stuff? That's back-end jazz, right? I don't need to worry about all that junk. No, you do. Because on the front end, we're doing so much more now than we ever have been with things like Next.js bringing us closer to full stack. And if nothing else, honestly, just for your interviews, if you don't care about any of this junk, you're going to need to know this just for interviews alone. Now, listen, you can get totally far without knowing this stuff. I certainly did. In fact, a lot of people I know don't know anything about data structures or algorithms, but it will make you a better developer. Anyway, I hope I've introduced them in a way that makes a little bit of sense to you. Algorithms are everywhere. We leverage them all day long on the programs we use and write. They are using the maps we're using. They're on the social media networks we're using. It's a way for you not to reinvent the wheel. Go to the show notes, get the data structures and algorithms guide, and then look at the video for trees, which has some source code to get you introduced to binary search trees. Hope you enjoy that. And if you're serious about joining Parsity, by the way, also check it out and grab some time with me. Hope you enjoyed that, and I will see you around. That'll do it for today's episode of the Develop Yourself podcast. To learn more about becoming a software engineer with us, then check out parsity.io. If you're not quite ready for that, then jump into our dev30.xyz program, which is 30 days of working on your mindset, habits, and JavaScript skills. Totally worth it. See you next week.